Welcome again to our next tutorial. This time we want to work with our data which we produced. So for example with our radio telescopes. And a very famous format is the NetCDF, like already explained in the lesson. And therefore we want to talk about this NetCDF and we want to work with this NetCDF. And we want to use again real data. So therefore let's jump directly to the first question in our tutorial. So the first question is download a selection of the VGOS-DB files. VGOS-DB stands for Geodetic Observatory in VLBI, and it is the data format where all of the results from the VLBI sessions are stored. And therefore, you can directly get this VGOS-DB, for example, from CDDIS, NASA institution, or from the BKG in Germany. Their download page, you have to register, and then you get these files, so the result files. So download one of these VGOS-DB. I selected one, and I zipped it, so you can download it from the Moodle pages. For those of my students and for those who are just visiting the YouTube channel, I'm sorry about that. You have to register and you have to download directly from CDDIS, for example. So download it and use this real VLBI session with a Wettzell antenna. So here again, VGOS stands for VLBI Global Observing System Database, and it contains several files. So now you should do the following. Find the file containing meteorological info, check which variables are contained, read the values and plot temperature, humidity and pressure in subplots. So if you carefully watch the video about NetCDF, then you already get some hints, because I showed you there a sample exactly with this meteorological info. So therefore you don't have to check too many things, so you can directly use this file which I explained there in a very fast way, of course. And now we want to use it in more detail. So we want to find this file. So let's directly go into our MATLAB program. So if you unzip this file, you will find all of these files inside. They're all for one antenna, one of our Wettzell antennas. You will find one of these data sets for all of the antennas participating in a VLBI session where several telescopes around the world participate. And if you watch this, a very good hint is met.nc. So met maybe stands for meteorological information, so therefore you can directly work with this. And then we have to find out what parts or what variables, what is contained in this file. So therefore you can do the following: NCDisp. So in my case, I do a NCDisp on the whole file path, which I use to store my lesson data, and I open met and see there. So and if you do this, you will see the whole content. So let's zoom out. If you watch this, you see a lot of things, a lot of dimensions. For example, for the different character fields, you will see later on that character strings are difficult to store in this format. So the format is very much focused on, let's say, numbers and numeral data. And then you will see the station scan data, so the number of data. So we have 494 elements of data. And then you find a lot of additional variables, and you see these are informations or information about the session itself, create time created by the program, so the session, the scientific program, and so on. And then you will find TMC, rel hum, and at press. So this is the temperature in degrees Celsius, this is the relative humidity, and this is the atmospheric pressure. So we found all of this. If you watch this, then you have 494 elements, but just one row or one line or one row or one column. So you have one vector. For a plotting, you need more than one vector. You need the x-axis and you need the y-axis. So in this case, as the records are based on time, you need somewhere the time information. And this is the difficulty now. So where do we get this time? We can easily plot this. I show this in the lesson. So just take it and plot it, and then you have an equidistant plot scenario. But it's not the reality. It does not correspond to the reality. So because all of this information details are time tagged with the time when they were recorded. So therefore we need an information about the time. So let's search about this, and you will find here two things: time tag and time tag file. And then you can have a look into this. So let's first of all check time tag, for example. So that I don't have to enter all the time this stuff here. I create a path information, and I can jump to this path information so that I have NC file path which corresponds to the whole file path, and therefore I have shorter commands. So for example, I can do NCDisp just with NC file path, and then I get this information. Okay, so therefore I have an easier way to connect this. So let's have a look into time tag. What is containing time tag? So we do a NC read. If you don't remember, watch the video about this. Then we use the NC file path, and then we want to read the following. We want to read time tag. So let's have a look. And it reads the information into ANDs, therefore I have to print ANDs. So you see station scan. So it does not help me too much in this case. Therefore, let's have a look into the next. The next was time tag file. Time tag file might be a better solution. Time tag file. And if we write ANDs and maybe directly do the transpose so that we get a readable version, then it looks a little bit better. Maybe time utc.nc might be a file with the different time tags. So let's have a look into this. We change now the NC file path to this new time UTC NC, and then let's see again what is the content. So usually what you do is, if you get a new format, you directly read the description, the standardization, and then you know what is the content. But with this NetCDF, it's so nice because you directly can work just with this NCDisp, and you can directly check what is the content of the files. So therefore, let's do it, NCDisp, and let's directly read NC file path time tag file. Oh, I'm sorry. Of course, without time tag file. So now it's the correct thing. So what do we have here inside? We have here creation time and so on, a lot of dimensions. It directly fits, so we have again 494 elements, and if you scroll down you see second and JM or YMDHM. So Y stands for year, M for month, day, hour, minute, second. It's great. So we have everything what we need. So let's have a look. What is the content of this stuff? So therefore we want to, let's read the second. So we do this with seconds equal NC read. Again, the NC file path. And now we can read the second information. So if we watch seconds, then we'll see that it contains a list of seconds. And oh, what a miracle, if you do the same with y MDHM and you watch this, then you will get a list of the corresponding dates. So year, month, day, hour, and minute, and the corresponding seconds. So with this, you can work, and you can now create a timestamp for the different values of temperature and so on. So what do we do now? We have now this individual days and dates with seconds, and we have to create now a usable continuous row which we can use for plotting. So you have now different possibilities. You can create modify Julian day, all of the things, but you already know a very simple solution. What is the simple solution? Do you remember what we used for the different requests about time and search in the calendar? Yes, Posix time. So we start from the epoch, the epoch we start year 1970, and we count just the seconds. And MATLAB directly prepares everything for that. So it offers us everything for that. So let's use directly these mechanisms. And therefore we have to convert this into a continuous 494 elements long Posix time vector. And this can be done quite easily, because if we combine this with a second, then we can use this as a string to convert it to Posix time. And this is what we do now. Okay, so let's continue. So the first thing what I want to do is that I want to convert this into a version which is really usable also for or in the same way like the seconds. So what do? We transpose. And what we have now is this nice list. And if we add in the sixth column now the seconds, then we have a complete time tag. I don't know why it is not like this already in the NC file, but here in our case, if you want to work with it, it's much better to do this. So we create a new vector or a new matrix, let's say like that, where we combine the existing matrix with vector seconds. So now we have in the sixth column, we have now the seconds, so that we have a complete time tag for each individual information. So and now we can use the conversion. For the conversion, we need a time string in a special time date format of MATLAB, and therefore we have to use date time to do the conversion. So let's say time UTC is equal, and then we convert everything what we have inside here. We convert directly to a time string. So let's say date time, and what we do is we do num to string and we convert the year, month, day, hour, minute, so this matrix, with a special format. So the special format says that everything what is inside here will be formatted, for example, with typical C notation. The typical C notation says I have this percentage sign. Then I can say if I want to fill not given numbers with 0, for example here, if we have a 2, we want to have it with 2 elements, so with 2 characters, and the first one should be a 0, so that we have always a time string which is in the same length. So also, for example here, we want to have a 0, 1, so that we have always 2 letters here. In the first thing, we want to have 4 letters, so, and we want to fill it with a 0 if there is not enough number, or if there are not enough numbers available. So we do percentage 0, 4, and we have a decimal number. So this is the classic format in C, used in C, and therefore we can use it also here. Then we have a minus, so a year, 4 numbers, 4 characters for the year, and then we have 2 characters for the month, and then a minus, and again 2 characters for the months. And then we want to have a blank, and then we want to have again 2D for the hour, 2D for the minute, and 2D for the second. So I need automatically converts now our information from this matrix into strings. So we will have 494 strings with this format, where we have, for example, for the first one, 2019 minus 12 minus 02. Then we have a gap, a small delimiter, it's a blank, and then we have 17:01:24. And then we feed this into date time, so that we get a usable date time format. And we do this, and the result will be a list of 494 elements with this information. So what we also can do, I also noticed this time UTC, because if you watch into the file, you will always have the information about UTC, so that we really fix it in our conversion. We can tell that time UTC is really based on UTC. So we set the time zone to UTC. These are the usual time zones which you also find in the settings for the operating systems. Have a look which possibilities you have. You have UTC plus and minus an hour number, so that you can select your individual time zone. Or you have also, for example, time zone Amsterdam, Berlin, or whatever. So you have a different sets of the time zones. I define it really as UTC. And then you have the time in UTC. And then what you only have to do is you have to convert this into Posix time. And if you remember, in the search in the calendar, we already used this. We used Posix time, the function Posix time. So what I also change is that I want to have the format long G. So I define the format that I have the 64-bit format for this conversion. And then I say time stamps equal Posix time of time UTC. So if I do this, you see now I have a list of my epochs based on the Unix time or the Posix time. And then I set the format back to the standard format. Okay, so with this we have now the X vector available, and with this X vector we can now do the plotting. So remember, let's have a look and see this. Oh, wait, we have to change first of all the the file so that we have the file path again. So I set it back to Met and C. And then we can have a look into this file again so that we know which things we have to read. So we have to read temperature C, temp C, rel hum, and atom pressure. So let's do this. It's quite simple. Do you remember? We use NC read, temp C, and then read humidity, and read pressure. And now we have all data available. We have the x-axis, which is the timestamps part, a vector with 494 elements. We have the y-axis for temperature, we have the y-axis for humidity, and we have the y-axis for pressure. So now we can start with the plotting. So let's do figure 1. We create this figure. So I will keep this figure. So let's close this. And we should do some subplots, and therefore we have to create 3 subplots. The first one is for the temperature, the next one is for the humidity, and the next one is for the pressure. So therefore let's create the first subplot. Subplot. We have 3 lines, 1 column, and we want to plot the first plot. So we have 3 plots in vector, or here in 3 different lines, and the first one is the temperature, which we want to plot now. So what we can now do is we just plot the time stamps as x-axis and the temperature as y-axis, and voila, you have the data available. Let's beautify these things. So let's set a title and also the x and y labels. So I set the title temperature, I set the x label time in Posix time, and I set the title time or the y label time in degrees Celsius. Where do I know the units? So I know this from the additional attributes. You can also read the attribute, for example, if you want, and then use this attribute as a unit here. I just do it manually here, so because it's easier to explain here. But of course, you can use NC read attribute to read this units attribute. Okay. So this is the first plot. Let's do the next plot. So we want to plot now the second plot. So we have 3 lines, 1 column, and we want to plot the second plot. Again, we plot now humidity against timestamps. So timestamps is the x-axis, and we want to plot humidity. And it's great, we have humidity plotted here. Let's do beautification again. And finally, the same stuff for the pressure. And we have the data available. So, and these are real data. So these are the data from the radio telescopes. So isn't it nice that you have direct access to this now? Because with just, let's say, 3 commands from the NetCDF, from the simple MATLAB format, you can directly work with our data, so with our international data. and you can check if the scientific results are really correct. And this is science. So this is really science, that everybody has access to this data, that everybody can check this data, can work with this data, and it's so simple with this nice let's say formats. So MATLAB offers you everything for that, and you can directly work with it. You can also use Python, you can also use C++ or C libraries for NetCDF. So there's a bunch of tools to work with these things, and you can directly work on real data sets. So just register, for example, in CDDIS, and you get data. I think that's great. So let's do the second job for today. Again, working with this, because we also want to see to which directions our radio telescope watched for these times. Okay, so in which azimuth position and in which elevation position the pointing angles were defined to really meet the signals from the quasars. So let's have a look. The second subtask of this first task is find the file containing azimuth and elevation positions of the antenna and plot also these values in subplots. So there's a typical type again. So of the antenna. So let's have a look again into our data sets. If you watch again into our data set, then you will see that there's a file AL. So this AL will be something like azimuth elevation. So a good hint. So let's have a look into this. How do we get a look into such a file? We do NCDisp. Even if you don't know the format, we can directly do NCDisp. Oh, by the way, let's set again our path. So we set the file path to this NC file, so that the commands become easier. And then let's NCDisp this file path, and we will see there is an elevation information and the azimuth information. It's a theoretical one because it's just calculated out of the information which is used to inform or to program the pointing of the antenna, and not the real pointing. So the antenna has some adaptations, for example, refraction correction, to adapt influences from especially pressure, or atmospheric pressure, things like that. So these are the theoretical positions, but they help us to check to which directions the antenna points during this 24-hour session, for example. So again, let's have a look. We have again 494 points. It's clear because it's the same session, and we can use L theory and azimuth theoretical. The units are radian, so for human readability I want to convert it to degree, of course. So let's have a look into this. Let's read the data and let's work with the data. Reading the data is quite simple. You remember we want to use NC read, and we read azimuth and we read elevation. I don't delete the data for the x-axis, so I keep this data for the x-axis, the timestamps. So therefore I did not delete the stuff here. And I have now azimuth and elevation available, and if you watch into azimuth, you will see that it is a list of two elements. And if you watch into this, you have radian and you have radian per second. So I don't like this style too much because it would be much better if you have different unit information, because now you have to parse this information again for the individual, let's say, columns. It would be much better if you would have just single elements, but it's like it is. But we know we have radian per second, which means we have a speed there. So we have this starting position, and then we have a speed so that we know to which direction we have to move the antenna. We just want to get the information about the starting position, so therefore we just have to use this first row here. So let's use this first row, and let's directly convert this information, this radian information, into degree. MATLAB offers you everything, so don't program your things yourself. First of all, check what MATLAB already offers. There's a function rat2dec, and we can directly use this. So we convert the azimuth position into degrees. So we take the first line, the whole line, we convert it to degrees, and then we directly transpose it so that we get a nice single vector, a column vector with all of our degree values. You see, these are the degree positions. And we do exactly the same, of course, for the elevations. And that's it, what we have to do. This is the whole thing, what we have to do to be able to plot this data. Therefore, let's create figure 2. And let's work with figure 2. So I close this again. Let you directly see the results. Okay, we want to plot two informations, so therefore we can directly set a subplot with two elements. So subplot with 2 lines, 1 column, and we want to plot the first one. And let's plot, of course, again the time stamps, and we want to plot now azimuth, theoretical degree. So if you watch this, the antenna really moves around. So we have all positions. This is a good sample because to avoid influences from the troposphere, an antenna moves in very short time periods to different sections of the sky, so that influences like water, vapor, things like that have no big influences, because we scan the sky, for example, in this case. So therefore it's a good sample. What is not so nice at the moment is that the output is not beautified. So let's do a beautification. Let's write again the title and the X labels and Y labels, of course. So we already know this. And of course, what is not so nice is this 400 and 0. So usually azimuth goes from 0 to 360 degree. Therefore, let's set the Y limit to 0 to 360. So we use Y lim to set this limit. So now we have 0 to 360, and now we see a nice plot where we see when we have 0 and 360 degree. And we do the same, of course, for the elevation. So we do the second subplot, and what you get is then a nice graph, also a nice scan of the sky. So we have all different elevations, and if you zoom out, you see now all of the different positions. So for example, at this position we pointed to 355 degree and a corresponding, for example, elevation. Okay, so it's quite nice. I think you have complete access, and if you really watch, this is just the plotting stuff, but the real use of the data are, in this case, 5 commands, and you can directly work with all of this data. You can directly check the data and work with this data, and this is a great thing. So let's continue with the next task. The next task deals with the creation of own files. So we want to now to create our own files based on existing files. Again, real data. Which real data did we use? One of the first lessons was about binary file formats and things like that. So these binary file formats are quite helpful. Do you remember altimetry data? They pack the information in a real dense mechanism to a file. So it's a very small, short file. The problem is that you really have to know what is the format or the structure of this format of this new format. So what is the structure? What is the structure of the records? How many records you read? All of this stuff. Okay, so therefore, let's compare this. If you remember, we stored this information also in a text file, and it was blown up, or it blew up the whole file. So it's a large file after this storing. So therefore, let's compare it to NetCDF. So we read the altimetry data from the binary file. Remember, you have this this script hopefully still available, and you use this script and you read the data, and then you convert it to NetCDF. You create your own NetCDF file. So let's do this. The question is, remember the altimetry files from a previous tutorial. Use one of the files, read its content, typo again, its content, and save the information as NetCDF file. Compare the sizes of the different files. So let's do this. So I opened this altimetry program which we created, altimetry step by step, and I just use now one single file. You can do it of course for all files, but it does not help too much here. I just want to compare the size of one file here. So I read one of the files and I read it and I do the plotting. So if we run this without a change, then you will see that we'll get a plot of the path of this satellite. So do you remember we had this in one of our first tutorials? Okay, so while we don't take care of this, we want to store all of this information which we have here. We want to store it in a new file, in a NetCDF file. So we have to read the data. This is already here, and then we want to store this information. So let's store this data by creating our own NetCDF structure. So let's add, after closing the file, the original file, we do the writing of the data as a NetCDF file. Okay, so what do we have to do? First of all, we have to create a file name or a file name for the NetCDF, and I would suggest that we directly use this file name and we just add a .nc, so that we don't have to do too many things. So let's copy the NetCDF file from the existing file name. So let's directly add it, so that it uses this table here, or this list of file names. And then let's use this, and let's add just the extension .nc. So with this, we have now a possible file name, and we can work with it. So the first thing is what we have to do. We have to think about what do we add. So the first one here is the Julian day, epoch 2000. Let's store this data. We have to know the dimensions. We have to name the dimensions. We have to name the variable, and we have to define the data type. I have to say that I have had some problems with the data types, even if you change the form, because different NetCDF formats allow different data types. So if you stay with standard data types like double, float, you don't have too many problems. I just want to show you in one sample change of the data type. In this case, I can use int32, even if for the, let's say, Julian epoch, it would be good to have a larger data type. But I just want to show you one sample where you can change the data type. So in my version, I had some problems with 64-bit data types, but maybe in newer versions it works. So what do? We create now in this file. So let's do it here. Sorry. We create now in this file a new variable. And this new variable, let's call it Julian day. In the next step, we have to define the dimension. So therefore, let's say dimensions. And then we have to define the dimension. So in our case, we have a single vector, a row or a column vector, and therefore we just have one dimension. So let's call this one dimension number of records. And let's define the size from the existing size of the data set. So here we stored all of the information records of the reading. So therefore we have all records available here. So we can directly derive the size of this vector from here. Size data set, comma 1. So that we have the size of the data set as the dimension of the records. And then this is the one sample where I want to show you the data type. Data type int 32. So that you can define the data type also here. As I said, I had some problems with data types here. So if you always use the double and the classic data types, character, single, and things like that, then it works properly. Otherwise, I had some problems. So with this, we created the variable, and now we can fill the variable with data. So we write the data to this file and to the Julian day. And we take it from the data set, and it's the first column, and therefore let's take this first column. If you don't remember anymore how this altimetry program worked and how the altimetry information is defined, watch the video, the according video to that, and you will see it again. Okay, so let's have a look that we also add additional attributes. For example, we can add the unit and also the information about the value. So let's directly assign it to the individual variable. So we use the same file name, we use the same variable or coordinate in this case, and we add the attribute unit with the information day. And the same we do for the meta information about the variable. We add an additional attribute info to the Julian day, and we set it to Julian day epoch 2000. Let's make it exactly like it is here, or like it was defined in the information file about the format. So if you run this now, we should get one additional file, which is stored here with the extension NC, and we can have a look into it. NC disp.nc, and you will see that it is now a file with a classic format, NetCDF 4, and we have 2646 elements with a data type in 32 in this case, and we have 2 units, day and info. And this we have to do for all of our data information parts or data record elements. So for latitude, longitude, height, and so on. Before we do this, you can of course delete the existing file, because you always can just create a variable once. So you can write different times, but you have to create it once. So therefore, as I just want to show you the general practice, I have to delete this file. You can delete it in the program, of course. I do it manually here. So let's delete the file, and then let's continue. Let's continue with latitude, which is the second column in our data set. So we create a new variable, latitude, with the same dimensions. I don't define a data type here anymore because MATLAB makes it right. So MATLAB does everything correctly with a simple interface. And we write the second column from our data set. And of course, we set the unit and the additional information. So let's run it, and you will see it will create now two variables. Now we have Julian day and latitude. We have the dimension number of records, and this we have to do for all of our elements. In this case, for all of these 20 different record elements. So I do it manually here for all of the elements. I don't explain it in detail anymore because it's just always the same stuff. In this case, 20 times the same things. So starting with latitude, which we already did, longitude, height, range, standard deviation, wave height, ocean tide, earth tide, inverse bar effect, wet drop, dry drop, ionosphere, mean surface height, and so on and so on. So let's store this. Let's delete the existing file and let's run it again. So if we watch into this file, then you will see that we have now these different data sets with all of our information. And if we now compare it, so if you compare this file with the same corresponding file here, then you will see the size is 4 times of the original size. Why is it like that? So why do we have this situation? It's exactly because we have now a mixture of additional meta information and the pure binary information. So the smallest, the slim format is really the binary format, but you need additional information. So you need this additional format description. With this format description, you can write your program to deal with it. With NetCDF, it's a standardized format. Therefore, you add also type definitions so that different computers with different, remember, big endian, little endian, most significant bit, least significant bit organizations can read this data. So you're not dependent on a special operating system. So this is the first thing. So type informations, additional informations about these types are stored in the file. Then all of this additional information here about the structure, about the sizes are stored here. So things like that. So you have a little bit more information. You have also the meta information as part of the file. And therefore, the file got a little bit more volume. So it's a little bit more size. And if you compare it to the text file, you will see that it depends on how many data you store there. So it depends on, it can be that, for example, that ASCII file is smaller. It depends on how you name the things in your ASCII file, or if you have just a table. So it depends on. If you have just a table in ASCII, you need additional information, things like that. So you always spend, let's say, processing time to reduce the size and you always spend size or volume if you want to reduce the processing time. This is again a connection to the algorithmic part and to the evaluation of the speed and performance of algorithms. So you see, you have a lot of connection points. You have a lot of connection points between lessons, and you have also a nice possibility to deal with own data, to deal with also data from the scientific communities, where NetCDF is very common and very famous. So that's it for today. This is almost our last tutorial. So we'll see each other for the next lesson. Stay safe and bye-bye until then.